you guys! Welcome to lab report number 4, Spring Oscillations. The purpose of this lab is to 1. See if we can predict motion by observing the motion of an oscillating spring and modeling this observed motion using known physics principles, and 2. Determine whether the energy principle is satisfied. After completing this lab, we found that the model we create does predict motion and the energy principle is satisfied. In this lab, we will discuss relevant physics principles we will be using, such as Newton's second law, Hooke's law, and the energy principle. We will also observe the motion of a spring using tracker analysis. After this, we will use physics principles to model the observed motion in Python and discuss any relevant data, such as models or graphs that come about as a result of our model. And finally, we will end by discussing final questions. There are 3 principles we will be using within this lab. The first one is Newton's second law, which states that net force equals mass multiplied by acceleration, and by extension the final velocity equals initial velocity plus net force over mass multiplied by change in time. Since we are dealing with springs, the second law we'll be using is Hooke's law, which states that spring force equals negative spring constant multiplied by the change in the spring's position. And finally, in this lab, we will also be talking about the energy principle, which states that the total amount of work is equal to the change in energy, which is equal to the change in kinetic energy plus the change in potential gravitational and potential spring energy, where kinetic energy is equal to 1/2 mass times velocity squared, potential gravitational energy is equal to mass times gravity times the height of the object, and potential spring energy equals 1/2 the spring constant times the change in spring's position squared. And now on to the lab. Okay, so really quickly, here's our video and tracker. We can see we set the coordinate plane to start at the beginning of where the spring starts, and we set the spring to be 0.7 meters long. And when we run the video, we get a list of times, x position, and y position values, and that's really what we need to pull out of this lab, along with the 2 graphs it gives us for time versus y position and time versus x position. Okay, so now we need to use the information from Tracker to gather some initial calculations. First, we need to find the period of oscillations, which we do by finding the time interval of 3 periods and then dividing by 3 to get that our period equals 1.524 seconds. Then we need to determine the spring stiffness, which we can calculate by using the equation spring stiffness equals 4 times pi squared times the spring's mass over the period squared. When we plug in the necessary values, we get that spring stiffness equals 6.83 newtons per meter. Finally, we need the relaxed length of the spring, which we can find by using the equation final length minus mass multiplied by gravity over the spring's stiffness. When we plug in the proper values, we find that initial length equals 0.123 meters. And now we can begin to do our model. Okay, so to briefly go over the more important parts of our code, in the code we have to start by setting up initial conditions. So we set the ball's mass, initial position, spring constant, and spring's unstretched length equal to the values we gathered from our tracker analysis. The final position is found by subtracting the ball's position from the spring's unstretched length, and the total change in distance is set to equal the initial length of the spring subtracted from the magnitude of the spring's final length. Next, we have to calculate the forces acting on the ball and update its position and velocity. To do this, we calculate the force of gravity and spring force and add them together to determine the net force acting on the ball. And once we know the net force, we can then use it in Newton's second law to calculate the updated velocity and position values. Because we need to determine whether the model satisfies the energy principle, we have to calculate the energies of the system. We do this by using equations we discussed previously to find the values for kinetic energy, potential gravitational energy, and potential spring energy at our ball's new velocity and position values, and then finding how much each of the values has changed by subtracting the previous values from the newfound values. Okay, so when we run our code in Python, we should get 2 windows that come up. The first window is a model of what we observed, with a blue ball representing the predicted motions from our code and the red ball representing the real motion of the object. We also get a second window which shows a graph that compares the real motion, which is the red line, with our observed or predicted calculations for the motion, which is the blue line, so we can compare the 2 and see how accurate our program is. As we can see, the model data, which is the blue line, appears to closely match up to the object's real position data, which is the red line. However, as time goes on, the lines appear to separate more and more from one another. So why does this happen? This is likely due to factors not being accounted for within our model, such as air resistance, which would act upon the ball and the spring and cause it to move not in perfect oscillating motion. Another reason could be due to human error lining up the point mass within tracker. Our first discussion question asks us to explain whether a model satisfies the energy principle. Our system is a closed system, and thus no energy is being added to the system as time goes on, so in accordance with the laws of the conservation of energy, this should mean that the total change in energy of the system is equal to 0, and as we can see from the graph, the yellow line representing total change in energy is always 0, and thus satisfies the energy principle. Okay, so for the final question, they wanted us to compare the period for the x and y direction of the object. So in the x direction, we found that the period the object moved was 1.651 seconds, and in the y direction, a period was 1.524 seconds. This means that the period in the x direction was about 1 second longer than the period in the y direction. So why are they different? This is due to the differences in the forces acting upon the object in the different directions. In the y direction, there are two forces acting upon the object, spring force and gravitational force, but in the x direction, there is only one, being the spring force. This causes for the object to move slower in the x direction than it does in the y direction.